get that. Me clear.
Alright, so our stage 2 will start now, and again, for the opponent to challenge the recorder.
statement says place a ruler on the edge of the table and throw a ball at its three ends, the ruler will fall. However, if you cover part of the ruler with a piece of paper and repeat the throw, then the ruler will remain on the table while the ball will bounce off it. So the key points we think it is important is the causes of ruler movement on the table, the motion of the ball, and the edge cases such as whether the ball or ruler is extremely elastic or non-elastic. So here the situation that you see is the situation that we define as the normal situation. So this means that the ball hits the center of the ruler on this axis that penetrates the hard point. And as you can see, when the ball hits the ruler remains on the table, which we define as the ruler did not completely leave the table for a long section of time. And at the meantime, when the ruler moves up, the volume under the paper increases, so that causes a decrease in the pressure, like the graph shows. And here are our parameters. So D is the length of the ruler extending beyond the table over here. And the small h is the height from the ball to the ruler. And the capital H is the critical height of the ball when the ruler starts to fall. And then the delta P is the pressure difference under the paper when the ball hits the ruler. Then here's our experimental setup. So the laser pen, the RF bar 3-point clamp, and the ball pen is used to adjust the position of the ball. And the ruler and paper over here we place on the board. We place on the board that which we use as the table in our experiments. And then over here is the relative pressure sensor. So to measure the relative pressure under the paper, we dug a hole in the board so that we can tuck the tube on the relative pressure sensor into the board. And here, the information in the brackets are the specifications of the ball, ruler, and paper. And you can see the material of the ruler is acrylic. Okay, so now for qualitative theory. Okay, so there is a common misconception that the ruler doesn't fall because of the atmospheric pressure. But instead, if we calculate the atmospheric pressure, we can see it is over 1,000 kilograms, which is very unreasonable. The reason why this is not true is because there's still some air under the paper, which means it is not vacuum. And so if we investigate in researches in a similar problem called ruler break, it has revealed that the correct reason for the ruler break is not the atmospheric pressure, but instead it is the pressure difference under the paper that pushes the ruler back onto the table. Okay, so initially the volume under the paper is very small, but when the ball hits a ruler, the ruler moves up, causing the volume under the paper to increase. And then according to the Boyle's law, when volume increases, the pressure decreases. So this causes a pressure difference between the top of the paper and the bottom of the paper. So if this pressure difference creates enough torque, the ruler will not fall off the table. Now for a quantitative theory. We model the expansion under the paper as a linear. So the height of the center of the paper rises linear. And so you can see over here in the green box, you can see there's the cross section of the paper on both sides of the paper. And so we can calculate the volume under the paper as a function of time. So over here, there's a function of the height. And here's a function of the area. And here's a function of the volume, which equals area times the length of the paper. Okay, so and now we can apply some laws to numerically simulate the physics scenarios. So now we can take a look at the initial conditions. So the pressure here is the atmospheric pressure, and the height is the ruler's height itself. Yeah, and here are some other parameters. And then for the ideal gas equation, we can use both Pv equals nRT or Pm equals rho times RT to model the behavior of the gas. And then now we can apply the Bernoulli's law. You can see in the blue box, we can apply Bernoulli's law to calculate the flow speed U of the air molecules. And this causes an increase in the number of air molecules, which is delta N. And so now we can use a Python program to iterate it and find the amount of air under the paper as a function of time. Now here's our numerical solution. So we can see the volume of the paper and the number of the air molecules under the paper increases with time. But the pressure under the paper first decreases and then rises back up. So we can see there is a pressure difference over here and there is a minimum pressure over here. Okay, so if we plot the pressure difference versus the velocity of the paper moves up, we can see the faster the paper moves up, the larger the pressure difference is. Okay, so next, so for a criteria for the ruler to not fall is the impulse created by the pressure difference, and the gravity of the ruler is larger than the impulse created by the ball. So and now for our experiment. So the table over here shows the relationship between D, which is the length of the ruler extending beyond the table, and H, which is the critical height of the ball when the ruler starts to fall. And so we can see when D increases, H, the critical height, decreases. But once the D is longer than 15 centimeters, the H suddenly drops to 0, and that is because the impulse created by the ball itself is enough to push the ruler down the table. And now, if we can use this table to get this scatter diagram. So again, we can see when D increases, H decreases. Okay, so over here, this diagram, you can see the relationship between D, the length of the ruler extending beyond the table, H, the height from the ball to the ruler, and delta P, which is the pressure difference under the paper when the ball hits a ruler. Okay, so in this diagram, we can see when H increases, the pressure difference also increases like this. And when D increases, the slope of pressure difference versus H also increases like the diagram shows. Okay, and then here is our experiment theory comparison. So this line over here is the blue line over here is the experiment line, and it is related to the trend line on the diagram over here. And so these two lines matches. And then here over here, the red line is the theory line, and these two lines also matches, which means our experiment actually relates to our matches our theory. Okay, so here are some other situations. So this situation over here, I call it the flip, which means the ball did not hit the center of the ruler over here on this axis that penetrates the power point. So you can see when the ball hits the ruler flips, and apparently it completely left the table for a session of time. So we define it. There's a fall of the ruler, and then this situation, I call it the glide. So when the ball hits a ruler, the ruler glides forward for a session of time. It first bounces off like this, and then it glides forward. And so we can see, again, there is a time when the ruler completely left the table, so there is also a fall in the ruler. Okay, so I'm going to talk about the edge cases. So for the edge cases of the paper, if the paper is extremely stiff, the ruler is less likely to stay on the table because the paper is too difficult for the ruler to lift up, and so it is hard to create a pressure difference that is large enough to push the ruler back onto the table. So vice versa, if the paper is extremely soft, the ruler will be more likely to stay on the table. And then for the edge case of the ball, if the ball is extremely elastic, the ruler will be less likely to stay on the table because the contact time will be too long and the force that the ball acts on the ruler will be too small to lift up the paper and create an air pocket. So it is hard for us to create a pressure difference that is large enough to push back the ruler again. So it is less likely to stay on the table. Again, vice versa, if the ball is extremely close to a rigid body, the ruler will be more likely to stay on the table. And last, the edge case of the ruler. So if the ruler is extremely elastic, the ruler will be less likely to stay on the table because the ruler will produce an extra elastic force causes the ruler to act like a spring and it'll bounce itself off the table. So vice versa, if the ruler is extremely close to a rigid body, the ruler will be more likely to stay on the table. Okay, so for our conclusion, first, the reason why the ruler remains on the table is the pressure difference under the paper. And then when D, the length of the ruler that extends beyond the table, increases, the H, critical height, decreases. And then when H, the height from the ball to the ruler, increases, the delta P, which is the pressure difference, increases also. And last, when D increases, the slope of the pressure difference versus H increases. So again, there is our line of experiment and theory. Again, our experiment matches with our theory. And that's all. Thank you.
So for the opponents and professors.
So I have a few questions about the report. First of all, I would like to talk about, I think there's a page where we talk about, we calculate the flowing speed of the tennis ball as the square root of 2gh. So do you consider this is resistant to that speed?
We didn't consider.
Okay, thank you. So I would like to ask specifically about the glide situation. Oh, it's okay. So do you consider the material of paper as a factor of affecting this friction coefficient between the paper and the ruler?
We didn't do it experimentally, but we did consider it in the edge cases, as we mentioned.
Okay. So I would also like to ask that I didn't see specifically you discuss about the area of the paper will affect to this phenomenon. So can you explain why didn't you include that parameter?
Wait, let me change. So and the area is this part of the paper. So I did use this equation to calculate the area.
Okay, so do you think relevant parameters about the ruler, such as the thickness or the width or the length of the ruler, can affect this phenomenon?
Yes.
Okay, so do you think that the velocity of the ball falling to the ruler can affect the duration time, or do you think that this duration time is mainly affected by the elasticity that you mentioned in the PPT?
I think they both relate to.
Okay, so I'd like to discuss that further later in the later discussion. And also, because you mentioned plenty of times that you consider the ruler falling down. So do you think it's possible if you can discuss about this boundary condition of the ruler falling down?
Boundary
Right,
condition.
time is up. So the opponent has 3 minutes for preparation. Please speak.
Honorable judges and worthy opponents, this is Team Me1 opposing Quantitative for Team Ruler Trick. So, proper statement is basically placing a ruler on the table and the ball falls down, and in some circumstances the ruler will fall due to the pressure difference. So, the reporter focused on the causes of the ruler remaining on the table, and also the motion of the ball, and also the edge causes such as elastic and unelastic material. So, summary for the report that the ball hits the middle of the ruler wouldn't fall. And for they established a really good qualitative analysis about atmospheric pressure and negative pressure, which cause enough torque to resist force. So they also established a quantitative analysis about the Bernoulli's law and airflow, and also an ideal gas equation. For the experiment, they find the critical height of this phenomenon, and also the 15 centimeter will be the boundary condition, and also ruler's length increases, height decreases, change of pressure decreases, and the stiffness will cause the ruler to fall, and the elastic ball and the elastic ruler also cause the same results. So for the pros and cons, I think that the reporter has a clear demonstration of the phenomenon, and also clear consideration of the boundary condition, and has a clear image to explain the theory, including what happens when the paper actually flips up. And also, however, about their cons, I think the lack of consideration regarding those different parameters in normal condition, and also lack of quantitative consideration on the different boundary condition, and also lack of explanation on the difference between theoretical and experimental data, and also lack of relevant parameters to the theory. So here are the discussion points that I would like to discuss later. First is the different situation of the falling ruler. I think it's really interesting that the reporter actually proposed several circumstances that they can be considered to be falling down the ruler. So I would like to discuss further about this circumstances and how did they fall. And for the theory part, I would like to discuss about this velocity, the velocity of the ball before collision, and its relation to the contact duration of time. So I believe that there should be a certain relation between these two. While the opponent didn't specifically consider this velocity condition, instead in the report they actually demonstrate this elasticity effect. So I would like to discuss more about that later. And also for the bending moment, they do mention this elasticity effect, which is related to the bending moment. Well, I believe that this bending moment is actually related to other parameters, such as the ruler's width and the ruler's length. So, and also they mentioned this isothermal process that's happened during the paper is actually flipped up. So I think it's really good that they actually established a process that happens during when the paper is lifted up. Well, I would like to further discuss about that. And also, for other discussion points, I would like to discuss the material of paper, which can cause some friction to increase or decrease. And also, the relevant parameters about the ruler. So next, I would like to invite the reporter to the stage.
Okay, so first, can I clarify something? So the ball we use is actually not a tennis ball. It is a ball that is quite elastic.
Okay, that's my bad. So, first of all, I would like to discuss about the different situation of a falling ball, because you mentioned when the ruler actually falls down and when the ruler glides and it slides.
Like I mentioned in my report, the only definition I said about the ruler's law is the ruler has completely left the table for a session of time. That is our definition of the fall of the ruler.
Okay, so what do you think that causes different situation that satisfies the condition you just mentioned?
Okay, so in our experimental setup, I think you've seen that I use laser pen to check where the ball will fall, but I still cannot make sure that every time the ball falls on the same position on the ruler. So in this situation, the flip, why it causes is because the ball didn't hit the center of the ruler on this axis. And then for the glide,
I totally agree with you about the flip, but I think that should be some kind of circumstances that doesn't really fit your prominent statement. So I don't think that's necessary to mention it here since it's experience data that can be
Okay,
excluded.
so the point why I mentioned these two situations is I just want to say that this phenomenon is actually very complicated. So it's not every situation can fit our theory.
Okay, so can you explain the glide?
Okay, so the glide. Okay, actually, I every time during the experiment, I want to make sure that the ball hits this this dot, the first yellow dot. On the ruler, can you see that? When the glide happens, the ball often hits like the second or the third yellow dots on the ruler. So that's I think that's why the glide happens.
So I would like to invite the opponent on the stage. Can I use the blackboard? So, in my opinion, I think that this boundary condition is actually formed in the relationship between the friction between the paper and the ruler. That theoretically speaking, if there's a table here and there's a ruler, and it's tilted due to the ball collision. You consider that the paper hovers here, and when this gravity force actually overcomes the friction between the paper and the ruler, and it slides down, you have to consider this as falling.
We do not consider it in our theory, but I think it does affect a little bit. And because when the ruler moves up, it moves like this, so it's like there's only a
little friction.
A little friction, yeah.
I believe that your theory actually covers most of the circumstances, but this kind of detail could affect small samples of the experiment. So I think this is something that we may consider in the future.
So I agree that it'll be better if we add the friction into our theoretical model.
Okay, so next I would like to discuss about the velocity and its relation with the contact duration. Because I came to notice that, I think that the first part of the report, you did mention that this duration of contact is,
The velocity.
I mean, the delta t is close to zero. So is that a misunderstanding, or you actually need that?
But you can explain it again.
So the ball's contact time delta t during the collision. So because I believe that this delta t can largely affect this rotational energy or angular momentum that this ball gives to this ruler.
So we kind of simplified so we can calculate more easier in our theoretical model. But we can see if we know that if the contact time is long, then the forces that act on the ruler will be small. So it'll be less
I
likely.
think even big.
Like,
If the contact time is longer,
I think when the contact time is longer, with like the edge cases we have mentioned, like when I said that if the ball is extremely elastic, the contact time will be long, right? So, and I said that I think when the contact time is long, the force will be small.
okay. So what do you think is the ball's velocity relationship with delta t?
Yes, I agree. And when the velocity increases, the delta t decreases. And
Yes.
so when the velocity is faster, the forces will be larger because the delta t is small.
Yeah, I totally agree with you, and I think this should be included in the consideration of the report. And also, next I would like to talk about this bending moment, because I captured a notion in the report about when you're discussing about the elasticity of the ruler. That if it's close to a rigid body, it's unlikely for the ruler to bend, as I saw in the video. I didn't clearly see the ruler bend, but in some cases, the ruler can actually bend a little bit, which dissipates the rotational energy that this ball gives to the ruler.
Yes, but in our theoretical model, we actually focus on this part of the ruler. So we didn't. I think this does affects, but it affects a little.
Okay, so you're focusing on that, but what I meant is that this ball gives this whole ruler a rotational energy. That part of it dissipates to act on bending this ruler, and part of it acts on lifting of the paper. That's what I meant.
So in our discussion of the edge cases, I think I mentioned when the ruler is extremely elastic, it'll be easier to bend, right? And we said it is like less likely for the ruler to stay on the table.
Yeah, I totally agree with you. But I think there are also other parameters that may affect this bending moment of the ruler. Because we all know if we're going to bend ruler, we need a second area of inertia, which is different from the moment of inertia where you're acting the torque. So, so this second moment of inertia should be related to both the widths and the thick widths and the length of the ruler. So I think in this case, I believe that this width of this ruler can actually also affect how the energy dissipation will react. So although it's true that this may not be the main factors that affect this phenomenon, I think you can put this into consideration to make your theory more complete.
So I agree that it would be better if we consider this situation. And I think you said we did not consider the wire and the length or the height of the ruler in our.
No, I didn't specifically mention that. I meant that it will affect this.
Okay.
So, next I would like to discuss about the isothermal process that you mentioned during the movement. So, because when the ruler actually lifts the papers up, I believe there will be some airflow that gets into it, which increases air pressure difference. So, can you elaborate on the isothermal process and what you meant?
You said when the paper lifts up, there will be air molecules.
Yeah, exactly.
So in the purple box, we actually use Python program to iterate it. So we have that equation to calculate the number of air molecules that floats in.
Okay, so because I'm also in the elasticity part, I think you mentioned the stiffness of the paper can affect the phenomenon.
Yes.
So I'm not quite sure that, because if it's more soft, as in your model, that it will form kind of low pressure below, so which causes atmosphere can be able to press it. So
It's actually the pressure difference.
yeah. Okay, so can you elaborate more on why this if the paper is soft, not soft? It will cause the probability of acting this phenomenon to be lower.
Okay, so I think in one of my diagrams, I showed that if the velocity of the paper moving up is faster, the pressure difference will be larger, right? So if the paper is soft, it is easier to lift up. So the velocity of the paper moving up will be faster, so the pressure difference will be larger. So that's why it can cause a larger pressure difference to push the ruler back down.
So when you say the paper is soft, you're not specifically mentioning this deformation of paper.
Can you explain more clearly?
I mean, because paper is softer, it's easier to create kind of a shape like this. However, it's
More round.
It's more easy to change its shape.
Yeah, so that's easier for the pressure difference to be produced.
Yeah, exactly. Because I believe that if it's formed like this shape, there will be less airflow that gets into these spaces, which creates a larger pressure difference. However, if the paper is not really it's not soft and remains this shape, there will be more space for this airflow to actually get into it, which creates a less pressure difference. So,
But if the paper is easier to bend, there will be a larger area under the paper. So so why do you think when the area is larger, the air molecule is
It's up from you to summarize the discussion.
So, in the discussion session, we first discussed a different situation of pulling ruler, especially when we discussed sliding probability of forming this phenomenon. And I believe that this can be into consideration that we also need to consider the friction between the ruler and the paper. And we also discussed about velocity's relationship with this contact duration time, which we both believe is an important parameters in this phenomenon, that this velocity can actually affect how the contact time between the ball and the ruler. And then we discussed about relevant parameters about this bending moments that might dissipate the energy that is act on the ruler. And we also discussed about the isothermal process that the opponent mentioned in the report, which I found is quite interesting. So,
All right, thank you very much. So the reviewer will ask questions, please.
So, my first question to the reporter is, from your observation of your eye, see that before you put the paper on the ruler, it has a slight deformation.
It's like that. You mean the paper slides
Yes.
back?
So, do you think that there will be a difference if you put the paper extremely flat or a little bit of deformation?
I think that does affect a little.
In what way?
So if the paper is not exactly flat, but there will be more. Initially, there will be more volume under the paper, so that causes the effect on the result.
So, what does the opponent?
I agree with the report.
So, my next question is, do you consider that air pressure near the ruler as a parameter that will affect this?
Near the ruler.
Yes.
Oh, I actually consider the pressure difference between the bottom of the paper and the
What I meant is air pressure near the ruler. Would it affect the phenomenon if you change the air pressure near the ruler?
Okay, I think I agree. I think it does affect.
Okay, so what is your take?
Yes, I believe that the facts, because it will increase or decrease the pressure difference between created in the process.
Okay, so my next question is, should the contact time be considered?
Yes, but we are kind of simplified in our theoretical model.
Okay, so opponent, what do you think that the contact time relates to in the experiment? Is it change what conditions the contact time change and overlap?
So you're asking what parameters can change the contact time.
And overlap.
So I think if the contact time is longer, it causes the ball to have more time to put some momentum or energy on this ruler. So in a most simple way to explain that is that if you gently place the ball on the ruler, it will definitely fall because the contact time is really long. So I think the contact time can cause a ruler to fall if it's long.
So the next question is, are there different parameters that will affect the ruler will fall or not?
For example, if the number of sheets of paper placed on the ruler will also affect, but I did not put it in my report because the data is not that complete.
Okay, so what do you think what is the difference between putting one paper?
So if I put 5 paper or 1 paper on a ruler, the 5 paper will be less likely to be lifted up and create air pressure under the
Okay,
paper.
so what is the difference?
Different for what?
Like if you put one paper or two paper, what will be the difference?
I think generally it won't make a big difference, but focusing on the mass of the paper.
All right, time is up. So the reviewer will have 2 minutes for the preparation.
so everyone, I'm the reviewer from TYPT. Today I'll be talking about number 2. So first of all, for the reporter, I think she has a clear observation video. And she also has numerous experiments to prove her theory. And in her presentation, she also showed some clear diagrams with labels. And she also included some mathematical models in her report to emphasize what she's trying to talk about. And she also has sufficient experimental data. But there are some areas of improvement where I think some units in the graph weren't labeled in her PPT, and some experiment variables were controlled by she observed that the paper seems to have a slight deformation before putting on the rulers. And next is there was a lot of parameters included in the model, but it wasn't experimented on very fast, point of concern. Last is she kind of lacks an explanation on the difference between the model and the experimental data. And next, as for the opponent, I think he has understood the reporter's presentation pretty well, and she also mentioned some flaws in her presentation, including the lack of consideration of the friction between the ruler and the table. And the opponent also understood the main focus of the problem statement. He also understood the theory of the reporter very clearly. But however, there are still some areas of improvement where the problems in the reporter's presentation weren't brought to attention. We think that's kind of big. And he also lacks in-depth discussion, most of which they were discussing about was already mentioned in the reporter's reports. And the opponent also focused too much on other parameters and not their experimental data. So as for the Q&A part, the opponent first asked what wasn't the area of the paper considered as a parameter, and the reporter answered that in their model they already included that. So as for the discussion part, the opponent asked to clarify the different situations of the ruler. And the reporter said that different situations depends on the contact point of the ruler. Then they also discussed about the velocity and contact times relationship. And the reporter says that as the velocity increases, contact time increases, and vice versa. And the opponent suggests that it should be mentioned in her report. And they also discussed about whether the material of the ruler affects. And the reporter says that the bending moment includes energy loss. So my first question for them is slight deformation in the paper which we observed in the video. So the reporter said that it might affect the phenomenon because it will increase the volume of air under the paper, and the opponent agrees with the reporter. And my second question for them is, should contact type be considered as a parameter, important parameter? And the reporter says that it was simplified in their model rating. And the opponent says that contact type increases, the ruler is more likely to fall. And my next question for them is, are there certain parameters that will affect the ruler will fall or not? The reporter says that there are several other parameters, but the data was incomplete, so it was not included in their report, such as the number of papers stacked up. And the opponent says that the amount of paper might affect. And this is the end of my presentation.
So the reporter will be the concluding remarks.
So for our concluding remarks, first, the friction between the ruler and the paper is small, but we should have discussed it in our report. And the bending of ruler could be modeled using beam theory, but however, we measure the speed of paper rising from experiments, so we think that isn't that necessary. And then the contact time is an important factor, and we have measured it in our experiments. And then we actually we modeled expansion as isothermal because the air flowing in is at constant temperature. And then yes, the edge cases should be discussed. And then for the different, we have discussed the deformation of soft and stiff paper in our presentation, but however, we have opposite statements with the opponent. And then for the pressure near the ruler, I think the reviewer should clarify it more because I don't really understand the question. And last, for the initial volume under the paper, we think it is an important factor. That's all for our concluding remarks.
Thank you very much. question from you? Well, let me first give a question for you, starting from the order. It seems to me you mentioned you consider the bottom underneath the barrier is the isothermal expansion, is that right?
Yes.
And so my question is that, is it possible in any condition, people can see the adiabatic expansion? Is it possible?
To see what?
Adiabatic expansion,
Un-
no heat flow exposed.
yes.
Is it possible?
Yes.
Design experiment. If it is, please briefly describe.
Um, Could you repeat the question again?
Usually we consider expansion either in terms of isothermal, which is the one you consider,
Yes.
or maybe it can be the adiabatic expansion, where there's no heat flowing back and forth.
Maybe we should fix the heat flow into the system.
So maybe your some comments about the expansion of the underneath the table.
So, or actually, if it's possible to design an adiabatic process during the
Exactly.
So, I think it's possible if we contain the whole phenomenon in the box as no heat flow go inside and control the ball with a magnet force that by releasing the magnet, the ball falls down. And I think that will be more approximate to this adiabatic process.
I think we can build like a chamber or something and release the ball, just like I said, like with the magnet, so that we can consider different parameters in that will affect this.
I have a question. Okay. So, do you think the area in the paper, okay, the area where there is an air volume and the area where there is no air volume, is the portion, what kind of portion of these will affect the phenomena?
You mean the area in the paper?
Yeah. So okay, when you pour heat on the ruler, there's an area where air come in, and there's some portion, okay, where there's no air. If the paper is long enough, so there's some portion there's no air, and there's some portion there's air. So what would be the effect of those portions
I think we
affect this phenomenon?
I think we consider the area over here. You mean there will in some position there will be no air under the paper?
Yeah.
I don't think there will be.
If paper is long enough,
Okay, so we only consider the part where there is a pressure difference. So we only consider the part where there is air, and when the air, we only consider the part where there's air.
So I believe the air pocket remains the same, but as the area of the paper decreases, the part where there is no air will decrease. So I think that will let the ruler fall off more easily because as area decreases, the air pocket size remains the same, but the other parts that have no air will come smaller. So it kind of lets air to flow more easily. So I think that might let the ruler fall.
So I believe that we increase the area of the paper, it will have different points of the area that there will be air or not air. So which there will be a slightly pressure difference at each point of the area, microscopically. So I think it will definitely affect the phenomenon, but we can't really analyze it macroscopically.
Right. So if there's no more questions, we'll give the jurors about 1 minute to decide the final.
start with the reporter spread. And the grades are 7, 5, 7, 6, 7. Now here comes the opponent's grade. 6, 6, 7, 6, 7. And the last one will be the reviewer's grade. And the grades are 6, 6, 7, 5, 7. So for our next stage 3, I don't know if you all agree, I mean all jurors in the 3 teams, can we have only 10 minutes break? Or maybe you still sitting having 15 minutes break? If 10 minutes is okay,